In this section, we have learned how to balance a redox equation using the half reaction method. So let's take a sample problem and work through it, applying the steps that we learned in the previous part of this section. And here's the problem. We're going to write a balanced equation for this reaction shown in figure 2.1. And in this reaction, a deep purple solution of potassium permanganate is titrated with a colorless solution of iron 3 sulfate and sulfuric acid. The products are going to be iron 3 sulfate, magnesium or manganese 2 sulfate, potassium sulfate, and water, all of which are colorless. So let's write the formula, and then we're going to write the ionic equation. So here are we had potassium permanganate plus iron 2 sulfate plus sulfuric acid, and the products are going to be iron 3 sulfate, manganese sulfate, potassium sulfate, and water. So it's a long equation. And so that's the formula that we want to balance. And the next thing we need to do is write the ionic equation, which will make it even longer. So the potassium permanganate that we started with right here, okay, that one is broken up into a potassium ion and a permanganate ion. The iron 2 sulfate is broken up into an iron 2 iron with a positive 2 charge, a sulfate ion, and then sulfuric acid is broken up into 2 hydrogen ions and a sulfate ion. And then iron 3 sulfate is going to be, here's the iron 3, but with the subscript here of 2, we have to put a 2 in front here. So we already have some coefficients that we'll have to maybe adjust later on. And then we have 3 sulfates, so 3 sulfates, and then manganese sulfate. If sulfate is a -2, then that makes manganese have to be a +2. I think in the previous problem it said it was manganese 2. So just, but if you didn't know that, you could figure it out. And then potassium sulfate, there's 2 potassium ions and a sulfate ion, and then there's water. And water is a molecule, so we don't need to break it up into separate little pieces. So now we're going to assign oxidation numbers to each element and ion, and then we're going to eventually end up deleting the substances that contain an element that does not change its oxidation state. But we won't know that until we assign the oxidation numbers to each element. So potassium ion is a +1, and then taking manganese or manganate, I say, or permanganate, we know that each oxygen is a -2. There's 4 of them, so that's a -8, and we has to add up to a -1. So that makes manganese be a +7 up here. Okay, iron's a +2 over here. Each oxygen's a -2. There are 4 of them, that's -8, and it has to add up to a -2, so that means the sulfate has to be a +6. Each hydrogen's a +1. Sulfate again is going to be what it was before. Iron is +3. Sulfate again, what it was before. Manganese is positive 2, so we know here it's a positive 2. Sulfate is still the same ones that we had from before. Potassium plus 1, sulfate again, what it was before, hydrogen plus 1, and oxygen minus 2. So what we can see so far is that manganese has gone from a plus 7 to a plus 2, and iron has gone from a plus 3 or a plus 2 originally to a plus 3. So those are the two elements that have changed, manganese and iron. And we have a lot of sulfates that have not changed. Potassium hasn't changed. So we're down to primarily just going to be iron and manganese. So this is going to be what we're going to be working with. So we've stripped away everything else down to the part that really counts. And the plus 7 for manganese was attached to an oxygen, 4 oxygens in the permanganate, so we have to take the whole thing. Iron was by itself with a plus 2, and on the right side of the equation, iron was a plus 3 by itself, and on the right side, manganese was also by itself. So that's why we can get it down to just those 4 things right there. Okay, so now we're going to then write our half reactions from that. Now we will take the basic equation that we ended up with, and we're going to do the half reaction for oxidation. And oxidation, remember, is where the oxidation number increases. And we know that iron increased. It increased from a plus 2 to a plus 3. From a plus 2 to a plus 3. So that means it's been oxidized. To balance the mass, well, the mass is already balanced. We have 1 iron on one side, 1 iron on the other side. There are no oxygens or anything like that that we have to deal with. So the only thing that's left to do is balance the charge. So we have a plus 2 on the left side and a plus 3 on the right side. And remember, we want to add electrons to the side that has the greater positive charge. So we're going to add 1 electron to Okay, now we're going to do the reduction half reaction, and manganese shows a change in oxidation number, and it has been reduced. It's been reduced from a plus 7 to a plus 2, and we have to bring along the oxygen since manganese is part of permanganate. So it's we're going to have to adjust things because of that. Now, to balance it by mass, we have the same number of manganese, but we need 4 more oxygens on the right side. And since this reaction is happening in an acid environment, we're going to have to add water and hydrogen ions to balance out the oxygen atoms in this case. So we are short 4 oxygens for the right side, so we're going to have to add 4 water molecules to the right side. And then because we have added 4 water molecules to the right side, that has also caused us to have 8 hydrogens on the right side that we need to balance by putting 8 hydrogen ions on the left side. So at this point, we have the manganese at 1 apiece, oxygen at 4 on the left and 4 on the right, and 8 hydrogens on left and right. So we're balanced by mass. Now, the next step is to balance by charge. Okay, so let's look at what we have here. Manganese is a -1, and then there's a +8. So the total charge on this side right here is going to be a +7. And over here we have a +2. So the +7 on this side and a +2 on this side. So we have more over here than we do over here, a greater positive charge on this side. So we're going to have to add some electrons to the left side, and we need to add, it has 5 more positives, so we're going to have to add 5 electrons to the left side. So that will that'll cause us to have a -1 +8, so that's +7, and then plus a -1 of 5 electrons. That will make us have a +2, and that will balance out that. So we have the charges balanced as well. So now we're going to adjust the coefficients to conserve the charge, because in one of them we only used 1 electron and the other one we had 5. So we're going to have to adjust those. In oxidation we only lost 1 electron, but in reduction we gained 5 electrons. So we need to multiply the oxidation by 5, so it'll be the same as reduction. So there is the oxidation multiplied by 5. So we just put a parenthesis around our basic equation and put 5 in front, and then we'll distribute. The manganese one already has 5, so we're essentially multiplying by 1. So after doing that, we'll have 5 irons on the left side, 5 irons on the right side, and 5 E negatives on the right side. Okay, and now we can start canceling out some things that we have the same on both sides. So we can cancel out the 5 electrons on both sides, and so I think that's about all we can cross out right now. So now we're going to combine the ions to form the compounds back. So now we're going to put back all the things that were in our way when we did this. Every iron 3 sulfate molecule requires 2 iron atoms, and therefore the entire equation must be multiplied by 2 to provide the even number of irons. So that's one of the things that as we look at the equation, there is a problem. We need to get the irons to be an even number, because it says every iron 3 phosphate requires 2 irons, and it's an odd number, so we have to make it an even number of irons. So we're going to multiply that by 2 to make it even. And so the reason why we did that is we looked at iron 3 sulfate and we realized that that's going to be a problem, and so we're trying to solve this problem beforehand. And so we'll have 10 irons on both sides, and then everything has just been doubled. And then putting everything back together, we took out all those sulfates, so we have 10 iron sulfates here at the beginning, right here. The potassium, we have 2 permanganates, and each one was with a potassium, so we had to put back 2 potassiums. So that takes care of this part right here. And then on this side we have a total of 16 hydrogens, and each hydrogen was attached to a sulfate, and it takes 2 hydrogens for every sulfate. So out of 16, that'll give us 8 hydrogen sulfates. And then on the right side, we know that it takes 2 irons here for the sulfates. So this 10 is because we have 5 times 2 gives us the 10. So that takes care of this. And it was also combined with a sulfate, so we add the sulfate back in. The 2 manganese were combined with a sulfate each. So that would be 2 MnSO4. And then this part right here, you might have wondered, where on earth did that come from? Well, remember in the original equation it had potassium and sulfate. And over here we have 2 potassiums with the permanganate, so we have to have 2 over here. So when we added it over here on the left side, it caused this to be a 2, and then we have 8 waters. So that is actually the final balanced equation for this. This is one of those equations that if you were to try to sit down and balance it on your own, just by inspection, the only way we knew up to this point, it would be quite difficult to do because there's so many little details you wouldn't catch if you weren't doing it by the half reaction method.